Good afternoon, everybody. I'm Anne McNamara. I'm the director of the Vivid Lab under the Texas A&M Institute for Data Science. I am delighted to welcome Dr. Anjali Tripathi to Texas A&M today and to the Texas A&M Institute for Data Science. Anjali is NASA's inaugural exoplanet science ambassador. She's the lead science communicator for NASA's exoplanet program. As an astrophysicist at NASA's Jet Propulsion Lab, JPL, with a background in computational modeling of exoplanet atmospheres, Anjali also designs new space missions and contributes to climate adaptation research. Anjali is a research associate of the Smithsonian and a science communicator for PBS and the National Academy of Sciences. She's been featured by the BBC, HBO, and TED, and has contributed to multiple books, including Science and Cooking, which is one that's on my to-read list, and The Tech That Comes Next. Since 2020, Anjali has served on the LA County Public Health Department's COVID data team, leading data visualization for vaccinations, and she chairs the UK Foreign Marshals Scholarship Selection Committee, Southwest US region. Anjali has served in the White House Office of Science and Technology Policy, as acting director of the National Science and Technology Council, and in the US Department of Agriculture as a White House Fellow. Anjali earned her PhD in astrophysics at Harvard, her MPhil in astronomy at Cambridge, and her SB in physics with a minor in applied international studies at MIT, which will explain all the international travel everywhere. So Anjali, thank you for coming. We're delighted to welcome you here. We're very much looking forward to hearing what you have to tell us this afternoon.
Thank you so much, Anne. And thanks to everybody in the room and online. As you heard, I have sort of a varied background. And so it's delightful to see colleagues who I've met at computer graphics conferences who I've worked with in agriculture. You will quickly see talking in the chat that there's a lot of possibility out there and lots of ways to get involved. And so what I'm telling you about today is a little bit about my work in that role of being NASA's exoplanet ambassador and how we think about data a little bit differently than you might currently do. So I actually want to take a moment and start with the mission and the vision of NASA, because when we talk about NASA, if I just put up the meatball, if I go out and give the stickers to anybody, you will have people instantly recognize the brand. I've actually tried this on every trip I've taken in the past couple of years, and on every day of every trip, whether I was in Norway, Turkey, Greece, Japan, Indonesia, or Taiwan, the places I've been in the last year, on every single day I've found someone wearing something with a NASA brand, which is sort of remarkable to me. So when you think about NASA, you have an idea in mind, but I think it's important to step back and say, what is this, right? Because yes, NASA is about space, but the vision is that we're doing so, we're explorers of the, sounds great, the secrets of the universe for the benefit of all, right? Thinking about why we're doing this, right? The mission is to explore those unknowns, but then to have innovation for the benefit of humanity. You're inspiring the world through discovery. And when we're thinking a little bit about what do we do as scientists, what do we do as people who work with data, there is the day-to-day of actually turning the crank and getting it done and producing the machinery to get to that paper, get to that output. But why are we doing this, right? Why are we striving for some impact? Why are we innovating? And so thinking about what I would talk about here with all of you, data science, I know many weeks you have talks about algorithms and sort of latest and greatest data sets. And when Anne reached out to me, thinking about visualization and the arts, I thought this would be a great opportunity to talk about how do you actually go that last mile of once you've collected the data, once you've processed it, what do you do with this? How do we make an impact? And what do we do when we don't have that data? So going back to the bread and butter of NASA, right? Most people will think of something like this. So this is Alan Shepard being the third astronaut ever on the moon back in 1971. And this is the classic picture you get from NASA, right? whether this happened in a soundstage, as some people might argue with me, or in real life, which I would think is the case, there's a lot that it took to get to that image, right? And we can play this game in all kinds of other ways for what's iconic about NASA. Some people look at this and they think this looks like a simulated image. It's actually not. So this is from the Lunar Reconnaissance Orbiter's view of the moon looking back on planet Earth. Now, granted, a lot of processing has gone into this image. When I gave this talk at SIGGRAPH, actually one of the people came up to me afterwards and said, "Oh, I'm so glad you showed this. It was so hard when we were doing the image processing to make the moon look bright and not have the Earth look purple," right? So they actually ended up compositing this from two different images together. So you can go and look this up. It's kind of an interesting case study of the processing. But I show this because, of course, we are studying the moon, which is hard to do from Earth. And actually, our most studied planet at NASA is the Earth. More satellites are in orbit around it, studying it in different ways than any other planet. We always have trivia for our interns at JPL, and they actually always think that the answer is Mars is the most studied. And that's because you end up, thinking about what you do at JPL. So JPL is one of 10 NASA centers. We are the location out in Southern California. It's the only one that's a federally funded research and development center in FFRDC. So I'm actually not an employee of the US government. I'm an employee of Caltech. And we are the space center that focuses on robotic exploration of the universe. So our biggest, some would say, claim to fame are, the Pathfinder rover, Spirit and Opportunity, Curiosity, and now Perseverance rover. And if any of you would like to come on a tour, I encourage you to come out and visit us. We do that. We housed about 50,000 people a year for tours. But there's a virtual tour that we created during COVID that has opportunities to go around the museum. That's what this is, as well as a lot of different sites. So just showing you all of these images, right? If I showed you a Mars rover, where did this come from? You would obviously say NASA. There are other nations trying to develop this work. The UAE and China are all exploring Mars at the moment. And it's one of these things that, again, the work of collecting the data is a lot, but how do you tell that story of what else is there? So I want to pause and say, you might think, well, I'm here in a data science institute, and I really don't care about storytelling, the communication. And I would say, that's sort of debatable, but fair. So I wanted to pause and say that this is the year of open science that's been declared, 2023. So if you have funding from any of those agencies that's listed up there, NSF, NASA, there is a priority on making your data publicly accessible. Like within NASA, we have something called SPD 41A. You can look it up, and those are all our policies on what data must be publicly accessible, what are the requirements, how soon can data be embargoed from a telescope versus anybody in the community use it. And there's a lot of work being done in this space. Whether you are in the Geological Survey, agriculture, health, all of these things, to really think about this, they call it TOPS, transform to open science. And so I see both this push, right, of making data out there more accessible for other people to do their analysis from a base place, all the way to that storytelling of I can show a 5-year-old a picture of an astronaut, and they can start to put it together as all being on the continuum of what our responsibility is with data. Because again, I think it's really interesting to say, oh, I've got this new telescope, what can I do with it? But it also comes with this burden, both of the public funds and sort of this big picture of what am I responsible for and how does that fit? And so I'm an astronomer, as you heard, by training. This is a lovely image from the James Webb Space Telescope, right? This is gas that is going to go on to create stars, planets. It's beautiful. I will not be able to show you what those planets look like. And it's one of these things that if you think what you're showing is data and communicating, points on a graph are great, but not being able to actually show you what those points are and saying, trust me, they're there, or having a little bit of a Santa Claus moment. And so I want to just pause and say, when we think about planets, what has NASA been able to show us in the past? So if we start at the sun and start moving out, you can see the craters of Mercury, right? We can see, this surface that looks totally unlike our own. You can see it's a wall and rock. This was taken with the messenger spacecraft. Venus, where this is an interesting composite image, you can see these flaws based on how it's been stitched together. So there is some global simulation superimposed with data from decades ago, from the Venera mission, from Magellan and Pioneer. you know, we actually have new spacecraft that are being worked on to hopefully go there in coming years. But again, that's a world where when you look at it, you can see it's quite different from Mercury, right? But even though Venus is often called Earth's twin because it's about the same size, it's, you know, that's not what the Earth looks like. You know, when we look at the Earth and all of the data we're collecting from it, this is data that I pulled from August, but if you go to climate.nasa.gov, you can actually see data from this week. You can see everything from how hot it's been this summer, right? And that sort of endless heat to the fact of tracking wildfires' impacts around the globe in carbon monoxide. So the fact that we can look at all of these different data products using different kinds of light, you know, we can see the soil moisture where we've got drought, west looking at the African continent, all of these things, that data, just by looking at it, is telling you something and helping you make better decisions. And so I'll let it play through just some of the other data, because part of what I do, and this was mentioned, I actually work in climate adaptation. So thinking about how do we turn this data into useful information for decision makers. So we just published a paper last week that includes people from NOAA for working with communities in the Maine, out to folks in the Netherlands who work with the dams and lakes. They're controlling sea level rise of how can you forecast what's going to happen earlier in advance by looking at the data. So, right, so Earth is our most studied planet, but like I said, a lot of people think Mars with, you know, where we're able to take selfies of our own spacecraft, which is kind of cool, right? So this is the Perseverance rover, which is also called Mars 2020 because it launched in 2020. Stored in its underbelly with this little helicopter that was underneath and it came out. It's the first time we have something flying on another planet. And the idea is thinking about the future of space exploration, right? Because it's not always going to be rolling around. If you have something that can fly and survey where's a good place to look, that can do a lot of work. And so in the future, when we're actually bringing back samples of Martian rock, I don't know if anybody saw in the news, OSIRIS-REx, right, brought back samples from not a planet just yesterday that we can study to understand the history of the solar system. We actually, this rover is going around and digging holes, drilling and coring them, that another mission in a few years will come by and pick them up and bring them back to Earth. And part of how it's going to do that is these drones are going to go around and pick them up. Like you think about your delivery packages from drones on Earth, well, same thing for Mars, which is kind of cool. So again, thinking about what we see of the planets when we actually explore with the missions, you know, some of what you see is just beautiful. I mean, it tells you a lot about the science. And this is a look at Jupiter with the Juno mission, different views of the storms on the planet. But of course, you can also have moments that seem a little profound. So is everybody in this room is in this picture. Do you see yourself? So you're actually right here. It's probably hard to see, but there is, I don't think it shows up very well on this projector, but if you look at a high resolution image, you'll see in the same way that you can see other dots here, this arrow is actually pointing at the Earth and the Moon. It's a photograph that the Cassini spacecraft took called The Day the Earth Smiled. And again, the fact that we're sort of coordinating and interacting, what we're thinking about our missions. So of course, Cassini has done lovely science studying the rings of Saturn, moons of Saturn, you know, the ice and gas. I mean, I love videos where you see moons interacting with the rings and the material moves in and out. But we have this really in-depth look where we can see what we're studying and also see ourselves in it. And so if you were alive at any point before 1781, what you knew of the solar system and its planets would have been those 5 planets beyond Earth, right? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus. But in 1781, that's when they discovered Uranus. And that's, you know, the end of the Revolutionary War. When we talk about planets, though, with school children, right? Like every 5th grader can start naming planets for me. It sounds like business as usual, everything has been decided for centuries in the past. But actually, it's only very recently that we have this view of the solar system. So if we look at the storytelling of the planets, you know, in 1801, another planet was discovered, Ceres. And some of you might be thinking, well, Ceres isn't a planet. Well, sure, we know that now, but we've had that in context. Whereas as we were making discoveries, we said, well, if you just plot the order of the planets, you know, one after another and their distance from the sun, then Uranus fits this beautiful power law. And Ceres fits this power law, so that must be the law. Planets must be, everywhere you find them. But you can actually see there's a discrepancy by the time you get out to Neptune. And so when it was discovered in 1851, they had to throw this notion of, the laws of planet formation presence out the window. But of course, they've had observations, so there was definitely a planet there. And you thought, okay, the data is always telling me the truth. Well, when we looked at how Mercury moved around the sun, it didn't match anything we expected because it had this strange back and forth motion that we call the precipitated Mercury. And you can see that we then said that there was a planet interior to Mercury called Vulcan, right? So does anybody know what happened in 1915 that made Vulcan no longer a planet? Okay, so in 1915 is when Einstein had his theory of general relativity. So the sun, right, is the most massive thing on this image in our solar system. As Mercury is the closest planet to the sun, it actually affected its motion, and that could be explained by general relativity. But prior to that point, you have all kinds of astronomers who said, oh, I have observations of Vulcan, and people believed it was there, right? So it's one of these things that very often we reinterpret our data, right? Ceres becomes downgraded as a planet, Vulcan is no longer there. But you can see that in the 19th century, this was a map for schools of the solar system. And so I show this just because when people think about controversies in the solar system, they tend to get all upset about Pluto. So, why is Pluto not a planet? I run a team for something that our team name is I'm Not a Planet Either, that's our logo, right? And it's calling on the fact that, to be a planet, as defined by the International Astronomical Union, you have to be round because you're large enough, gravity has made it such. So that's the second condition. It needs to orbit around a star, and then it needs to clear the neighborhood of its orbit of everything that's about half its size. So Pluto's planet is round, but its problem, and it's around the sun, is that its moon, Charon, is big, and so it doesn't move that. So, everyone has feelings about Pluto if they're above a certain age. When I go and talk in schools, which is some of what I do, I can tell you the kids these days, they don't care about Pluto. They are not devastated the way that some of us were. Just by a show of hands, how many of you have feelings on whether or not Pluto should be a planet?
I'm legit mad.
But you can see that, maybe people in the past had feelings about Vulcan, feelings about Ceres. And having those emotions, right, is a really good way to interact with this. But I think, one thing people don't have a lot of feelings about, and part of what I try to do, is to think about, well, what's the problem? Okay, so this is what we teach kids in school. You've got the 8 planets around the sun. The sun is a really important part because it turns out, if you look around other stars, they're their own suns for other solar systems, right? And so we call those planets outside of the solar system extrasolar planets, or exoplanets for short. And this is every object, every planet we can find around the sun. And so this is all in my lifetime, right? 1999, 1992, that we've started finding planets. And so what this means is that if you go out on a clear night here, every star you can see, and if you can go somewhere dark and see the Milky Way, basically every one of those stars is a sun for its own solar system. There are exoplanets that have been counted, and exoplanets that haven't yet been, but just in that one patch of sky, the Kepler spacecraft actually found thousands of exoplanets. So each of those colored dots, I'll flash back and forth for you for a second, right? You can see how much more dense that is, right, than when you look at that patch of stars. Every star has probably a few exoplanets. And it's kind of remarkable that when I talk to people, most don't know that these are out there. And so if we look at the number of planets we've found to date, there's more than 5,000 that we've actually confirmed. There are many more that we've detected, but of course we require secondary confirmation that it's there. And of course, there are about 100 billion stars in the Milky Way galaxy, which is one of 100 billion galaxies. So we're talking about a very large number of planets that are out there. So to say that planets are common is an understatement, but a really new discovery for astronomy. And when we characterize these planets, there's not a lot we can say about them, but we can generally say how big they are. And when we're doing this, we actually find that planets like Earth, pretty common. Planets like Jupiter, pretty common. Things a little smaller than Jupiter, more like Neptune, also there. But there's a whole class of planets, these super Earths, that we don't have in the solar system. They're bigger, and we don't see them. And we don't know why that is. There are some reasons. Some of my research has modeled what could be causing them. But the fact that we have so-called mini Neptunes or super Earths is telling us that what's out there has a greater diversity than what we see in our own backyard. Just like if you only ever looked at the wildlife here in Texas and never been to the zoo, or never been to other places, you might think everything looked a certain way, right? So if we actually look at the history of discovery, so this is going to plot the mass versus the orbital period, so how long it takes a year on that planet. Over time, not every planet we've discovered has a mass, so this is only a fraction of the 5,000 planets. But you can see that early on, when we were looking at this, it was easy to find planets that were bigger, right? Which makes sense because there was more gravity to affect the system, more light was being shifted, and also things that are sort of further from their star. Whereas if you're getting closer to the star, this can be a little hard. Finding a smaller planet is hard. So if we look at how these planets were found, that all of those yellow dots correspond largely to that patch on the sky I showed you from the Kepler spacecraft with a technique called transits. Another 20% or so come from radial velocities. So just to tell you what this is, for those of you who think about Doppler shifts, right? If you look at the color of the light that you're seeing, if I just look at that star normally, it's got a particular spectrum, but it turns out if I've got a planet in orbit around it, then that star has some motion, right? Because gravity. And so that spectrum of light is going to be shifted back and forth. And so that's why you see the color is getting shifted, whether it's moving towards or away from you based on that planet. If those of you want to know what it looks like to be an astronomer, it sounds very glamorous. I get to look at the sky, get to go to Hawaii. This is me in Hawaii at a computer in a building, right? Like, doesn't matter. And this is some data, radial velocity for planets. We can see this sinusoidal wave. This is an extra special thing. That's one that happens to line up in front of the star. But you can see, this data, not that interesting, but it's telling you that you've got a planet of a certain size. For transit, so you all, by the way, in Texas are very lucky. Like everybody at work with me in LA is coming to your great state next year. Because you've got partial eclipse coming up in about a month. And next year in April, there's a total solar eclipse where you'll see the path of totality come through. And out of curiosity, how many people have seen a solar eclipse of some form or another in their life? Okay, great. All of you should see the total solar eclipse next year, okay? But please, I guess, safety announcement from NASA, please do not look at the sun directly, even when it's getting dark. Get some solar eclipse glasses, take a colander and look at the projection on the ground, pinhole camera, the whole thing, just because it turns out that even as late as the 60s, solar eclipses tended to be public health issues because everyone wanted to look at them directly. So don't do that. But I like this idea because we understand that a solar eclipse is when the moon gets in the wrong geometry so that we can block out light from the sun. But a transit is just that concept when you're not actually blocking out the whole thing. So this is the International Space Station going in front of the sun. And this is a time lapse, so at different times. And that's what we call a transit, right? So a transit is when I look at the light of a star and it seems to keep dimming periodically. And it turns out that that's because I've got planets that are going in front of it, right? So each time that planet passes in front of the star, the light drops. And so if I actually, plot this over time, what you'll see is this characteristic dip as the planet goes in front of the star. And we can look for multiple transits to see, okay, is there a planet in front of it? How deep was the transit? How wide is the transit? Will tell us something about it. So that picture I showed you of me in Hawaii was looking at this star and planet system and called WASP-3b. Astronomers are not very creative in how they name planets. So you take the name of the star, WASP-3, and then you add a letter starting with B because the star is A. This is the first planet. You can see it's about twice the size of Jupiter as the mass, and this is a planet we found. So we can do more interesting things with transits. There's all kinds of cool signal processing, AI-supported work that's done on transit data, but this is one called TRAPPIST-1. It's a little red star, it's a red dwarf, about 40 light years away. And you can see as this movie plays about 20 days of data, that this very complicated signal is showing you that there are 7 planets in orbit around this star. So You can see there's all kinds of systematics you have to clean up. I'm gonna spare you from all of the nitty-gritty of the data processing. But what is interesting about the system is that it feels a little bit like our solar system, right? Because you've got planets that are the size of Earth that are around the star, and they're in the right area where liquid water could exist on the surface of the planet. Because this green zone that you see here on the solar system is where we call it the habitable zone. So the inner edge is interior to that, water would be steam on this planet. Exterior to that, water would be ice, right? So this is the area where the temperature is just right and the pressure and everything that you could have liquid water even possibly exist. And so when we look around a smaller star that's redder, obviously if it's not putting out as much heat, you need to be closer to the star. And so that's why TRAPPIST-1 system would all fit inside of Mercury's orbit. But it's still kind of interesting because maybe it's just a scaled version of the solar system. And so you'll often hear me talk about the habitable zone with your other folks in exoplanets. And we make Valentines in my office, right? One is you had me at habitable, which if you're gonna look for life beyond Earth, you first need to find a place where it could exist. Okay? You want it to have a surface where you can bounce on, because Jupiter, for example, there is nothing for you to just go through. And you need it to have water, which we believe to be the basis for life on Earth. Life could take other forms, but this is the one that we know can. So we look for those conditions, and the habitable zone is part of that. We can also go a step further, and we can look at the atmospheres of these planets. So when you have that right geometry for the planet to pass in front of the star, you can compare the light that you see from the star to the light that you see from the star when the planet is in front of it. And if you actually compare these two spectra, you subtract the star only from the star and the planet, then what you get out is that chemical fingerprint of the chemical that's in that atmosphere. So, right, what molecules are there, what's going on. And this is a way that we can tell. Right, say you could see chlorofluorocarbons in the atmosphere of an exoplanet, that would be an unequivocal sign of life, right? Because there is no way to have life, naturally produce that signature. And so already the James Webb Space Telescope, in addition to producing pretty pictures like I showed you at the beginning, has shown us different chemicals in the atmospheres of exoplanets that we've never seen before, such as carbon dioxide, which you might think like, carbon dioxide in the atmosphere should be really obvious, but it's something that we haven't been able to see with our telescopes to date. So that's a first. And so there is a series of telescopes that have, so Kepler and TESS are really in the planet finding business. Kepler is no longer operational, TESS still is. It tends to find planets around little stars closer to home. And then Webb is actually going and following them up so that you can see what's there. So I want to just take a moment. This might be hard to hear. Hopefully the people online will get it. And if not, you can search for 5,000 exoplanets on YouTube. But this is actually a data sonification and visualization of all of the exoplanets that had been discovered as of last year when we hit 2020, when we hit 5,000 exoplanets. So take a look at where we see the planets in the galaxy and how they've been found. And look at the number when you were born and see how that compares. And the Kepler spacecraft launched in 2009. So look for that coming up. The data got processed and so data sonification is something we've been doing for both for exoplanets, black holes, all kinds of things, just as again, another way of interacting with this. So I started though this talk by talking about sort of how do we communicate things? What is the responsibility of sharing our data? Well, you've seen that I can tell you that planets get detected, and I can tell you about their size, maybe a little bit of what's in their atmosphere. But for most people, it's not real, right? They want to know, could I go swimming on this exoplanet? What does it smell like? What does it look like? And for the solar system, we've got these beautiful images, right? I mean, Webb took this picture of Uranus's rings. That for those people who didn't realize that everything after this point, like all of these planets have rings, even that was kind of mind blowing. But for exoplanets, I can't tell you what they look like. I am not a very good artist. So, if you said draw a planet, you might get that from me. If you said draw the solar system before 1781, you get that from me. There's a reason I'm not in school, my arts. But it's interesting because if you look at the maps that were made, right, this is the world centuries ago, all of the orbits, right, Venus, Mercury, Venus, Earth, Mars, Jupiter, Saturn, there's this lovely map and it feels very archaic. But there's something that they're doing here that's correct, that I actually really like. And that's what's going on in this upper right corner, because they are actually showing all of these other stars with planets orbiting around them, which for centuries later would only be when we discovered them. And so this orrery by Ethan Kruse actually uses actual data and is visualizing what those orbits are, how big the planets are, how far they are from their star, and is sort of comparing them to the solar system and what we know about it. And so just thinking about the fact that there are all of these planets out there, that we're not alone, is kind of remarkable. But also what I can show you about it is pretty limited because we can't represent it as anything other than these, circles, because I don't know what does it look like, what's going on. So one of the aspects of my office, so I wear a few different hats, but as the Exoplanet Science Ambassador, is we have a fantastic relationship with our artists, right? So on the right is a piece commemorating the first exoplanets that were discovered. And there's a couple of dates because it's not clear which was sort of counted as the first. 51 Pegasi b is not the first exoplanet. It's the first one that was found around a star like the sun. So that was in 1995, that won a Nobel Prize a few years ago. But there is this notion that when we talk about NASA, we're really focused on data and hard science. And people sort of forget that there's this whole history of art at NASA, right? So part of this NASA art program was H. Lester Cook, who this was a concept they did for a study on space colonies, right? Which sounds kind of ridiculous, but is also a thing that probably, I don't know if NASA isn't doing it, who should be. And he says, I hope that future generations will realize that we have not only the scientists and engineers capable of shaping the destiny of our age, but artists worthy to keep them company. And I think when we think about space, I showed you that picture of an astronaut, you see that kind of thing in Hollywood, in games, all of that. And it's a really important part of what we do. So if you were to come visit me at JPL, you would see that we have just a ton of art installations all over the place. But it's all grounded in data. So this, if I had the movie version of it, you would see the lights are representing data going to and from our spacecraft. So when they go up, we're uploading data, uplinking. When they're down, downlinking, and the volume of data that you see going up and down is portrayed by how many lights are going up. So when James Webb Space Telescope comes down, it looks like it's just raining white lights. Whereas the Voyager spacecraft, which is the furthest from Earth, it's like one light going up and down. On the right, this, over here, is showing a representation of two spacecraft called Grace that actually they track the movement. They track gravity on the Earth. So when one goes over a mountain, it gets pulled slightly, and the distance between them changes, and then the other one goes over that, comes back together. So by tracking the distance between these two spacecraft, for those of you who are familiar with the LIGO experiment, it's the same idea, this range. You can actually track how much water is under the ground, right? So this is used to measure aquifers and get a sense of how we're having groundwater depletion. This is showing you Antarctica melting, the graph that will be coming up there. So there's just a lot of interesting ways that we can integrate art into this. And I like talking about this a little bit because it's not something we do generally talk about, but I think it's an important part of the work that we do and how we think about it. So at NASA, a mission takes a long time from the start of when you first imagine it to when it actually flies and collects data. We're talking generally decade, 2 decades. we go through a number of phases. So you can see we go from pre-phase 8, so at the earliest stages, if anybody has an idea for what to do with $1 billion, NASA currently has a call out for what we do for the next Astrophysics Explorer probe. You can see it's due November 16th, so we've got time. And you know, that is not going to fly for decades. And so thinking about what you do, obviously you're going to have some sketches and mock-ups of what that looks like, but all the way through the end where we're talking, you know, this is sort of modeled after a Led Zeppelin poster, if anyone recognizes it, where Cassini, who took that selfie of us with Saturn, you know, we won Emmys and all kinds of things for our broadcast of the spacecraft plunging into Saturn's atmosphere. And this is one of its last pictures it took, and we gave people pins. But it's something that all the way from the earliest concept study through the design and actually flying it, we need to think about the art, because not only is this used in the earliest stages, this is the patent for the space shuttle, but we think we've got others, but also looking at things like Messenger, where I showed you that view of Mercury before. This is another one. You can see that this cover is from 1996, right? And this image is from 2018. You can see that's 22 years, right, have passed between when we conceptualized it to the end. And of course, you know, we didn't get a view of Mercury this up close, but when I showed you those craters before, that was not something that was necessarily known at that fidelity, right? Because you're always doing something new. And so the art is playing this role of connecting us both with what we hope to find to what we don't even know is there. So I'm just going to show a couple of examples from art before we go back to exoplanets. So this is as we're thinking about a new mission to go to Ceres, right? You remember Ceres is a planet or not planet, however you want to think about it. In the past, there was a mission that went there, and in the future, there's going to be something else. You know, Enceladus is this fantastic moon of Saturn that is the brightest object in the solar system because it's basically always covered in fresh snow. There's no dirty snow on Enceladus, and that's because there are volcanoes that are shooting out ice. Basically, it's cryovolcanism, which is kind of cool. I just filmed with the BBC a show about this, so next year you can watch me talk about it. But you know, this is actual data, right, from Cassini. And this is a model that folks, actually a former Imagineer who works at Disney, who's at JPL now, made this model, right, that we used in talking about it. And Enceladus has vents coming off of it with these icy geysers. And so that's the actual image on the left. And the big one is what our artists did to have this movie of it and to try and understand what's going on, both for our own understanding and communicating it to others. But if we take this a step further in that abstraction, you can actually see that they said, you know, visit beautiful southern Enceladus, because this is all out of the temple. It's, you know, more than 100 breathtaking geysers, the home of cold faithful. And so it's kind of funny, it's kind of cute. It's like a WPA style poster, but it's the sort of thing that I can actually communicate a lot of the science of what's going on and bring you in just through that art. Whereas you kind of needed me here to explain what was going on. And so coming back to this question of what do exoplanets look like and where are we going to get to? The sad truth is we are not going to have an answer to this question full of pictures anytime soon. So what we have to do is rely on, you know, other examples of what we have. So each of the stars drawn here, as we're zooming out of the Milky Way, is one that hosts a planet. So these are all of those, you know, 5,500 or so that you've seen. And, you know, this is a tool, by the way, called Eyes on Exoplanets. You can go to any NASA Eyes On product and have it render online for you. This one will show you, for example, wherever you're standing on Earth, since if you're somewhere in California, what are the planet hosts that you can see in the night sky? You might say, well, this isn't very interesting, right? Like, it's just showing the orbits of planets. And the answer is, yeah, I don't have a lot of data to show you. I have to write hypothetic visualization on it because I don't know if the planet's red. I mean, I can show you all kinds of data on how far away it is, and we can imagine if we could, you know, travel in a jet plane, how long it would take to get there. But if we're thinking about the future, we also, oh, and it's too bad that this closed captioning. Back away, I'm sorry. Oh, no, it's still there. Okay. Maybe. There. Okay. Thinking about stars, right, where you might look for planets, what are the different things we know about it? Because when we think about the future, I not only can't tell you the size of the planet, I can't tell you where we're gonna find it. It's sort of like if you think about Christopher Columbus or pick an explorer, what did it look like before you went there? What did you know about it, right? That's kind of wild. And so we have this whole project right now to think about, well, what does the future of exoplanet exploration look like? And what is the data we're gonna get? What is all of this going to be? So let's see. So these are three artist impressions of exoplanets, right? These are three very different systems. And you can see though that, yeah, they look like three different planets. Those kind of just look generic, right? Because what is the artist going to draw? When I show you these three posters, you think, wow, those are different, right? So if we go back a step, right, you can see that this is the view of the planet, and these are its two stars. This one looks kind of like Earth, and you can see it's in a system with lots of planets. This one sort of really big gaseous planet. And so our art department is pretty famous both within NASA and beyond for generating these posters. And so these come from my office. These are the exoplanets travel bureau posters. And what we tried to do is distill the idea of one attribute of each of these systems that we could communicate. So this planet is like a real life Tatooine, where, as if you're familiar with the Star Wars universe, where you're orbiting around a binary star. Turns out most stars in the universe are actually binaries, multiple stars. It's not just one star by itself. And so here we make the point, right? Your shadow always has company on Kepler 16b. Kepler 186f, you saw it's a planet that could be like Earth, right? And it's around this small red star. So maybe everything is going to adapt to dealing with red light. So if you look at how the plants photosynthesize and all of that, maybe it's different. And so we talk about where the grass is always redder on the other side. And that last one I showed you, right, is a super Earth. Remember, I told you super Earths are different, but if you think about, well, it's just bigger than Earth, but maybe it's got a surface and all that. Well, maybe that's a fun place if we're talking about traveling there. You know, that's good for skydiving. So all of this art is partly because I can't show you what's there. So if I take an example, right, like TRAPPIST-1, and you're thinking about, like, here I've got these 7 planets in orbit, and somewhere in the habitable zone, if I said, well, I need you to present that to people and I need you to get them excited about it, you can think about what is that one attribute you would have picked to represent it. It turns out that what our artists were most interested in was, what is it like to look up in the night sky and not just see the moon, right? But you see planets. So what we ended up with is this image on the right. And I was out at Fort Cavazos on Saturday. And I was talking to a friend's kids about this, and they were like, oh, wow, there are a lot of moons around this planet. And I said, oh, those are supposed to be other planets. And they couldn't wrap their head around that because, like, when you look up the sky, there are stars and there's a moon, right? And maybe you see planets, but they just look like bright points of light. But what's kind of interesting here, and not just that they're there, is that our team actually worked really hard on where do I have to be, which planet in the system do I have to be on, given how it orbits, to get everything lined up. How do we have to illuminate the different sides so that it's accurate? So there's this whole world of getting everything just right, and it's not just saying, oh, yeah, there's a planet, it's got others in the system, but how can we take our responsibility as NASA to be as accurate as possible and show people things? So, you know, if you go on that same Eyes on Exoplanets world and exoplanets.nasa.gov, you'll actually see you know, 3D renderings where we've taken this a step further, right? And now you can walk around the surface of that planet, so then you can see, here is that star, here are those other planets in the night sky. You can walk and see what that looks like. And so the fact that we're doing all of this, you might say, like, okay, Anjali came and showed me a bunch of NASA products. That's nice, no big deal. And part of that is because, yeah, they're kind of shiny, and maybe some of this will inspire you to dig further on it. But the other part of this is, again, I don't have data, right? And I'm not going to have data for many years on what this looks like. And even when I do get data on a planet, it's not going to be at the resolution of this picture. So how do you sort of connect that storytelling of what captures someone's enthusiasm, but also helps to understand what's there? And we don't have anything else. And that's part of the role of the art. So we've got different series. I'm currently working with artists on a new series that will be debuting in January. You can see we've got some horror movie posters that we call Galaxy of Horrors. So I want to just take us a step back and say, you know, this solar system, and this is the solar system as viewed through spacecraft. This was taken by Voyager, which is one of the 2 furthest objects from the solar system, from the Earth to date. And all of these, you can see it's just one pixel. This does not look as majestic as Saturn, as I showed you before. But this is really profound because each of the dots is a planet that we can see. And so when I told you what does an exoplanet look like, I can't tell you. Well, that's not technically true, because we have started taking pictures of stars and seeing things orbiting around them and saying those are exoplanets. You see this big black hole, and that's because in the same way when I'm driving at sunset and I'm getting blinded and I cannot see the cars around me, so I have to wear sunglasses or pull down the visor. It's the same thing here. You have to block out the starlight to see what's going around it. And so if we do that, and that video, by the way, shows like 12 years, you find 4 planets the size of Jupiter, and they're really far out from the star. 1 astronomical unit is the distance between the Earth and the sun. So these are very far away. But if we want to find a planet like Earth in the future, which is the goal, because if we're trying to find something like ourselves and life, that's what we want to look for. We need to get between the contrast ratio of a lighthouse, not just to a firefly, but if you're looking at bioluminescent algae in the ocean, to one of those, right? Single alga. And so we have work being done today. On the right is just the James Webb Space Telescope showing how we organize the mirrors. On the left is part of a star shape. So this is one way that we can actually block out some of that light to show you how you can get to seeing things that are dim, like an Earth-like planet, but also to bring that black circle in, right? So instead of having such a wide circle, to bring in that circumference so that I can actually see what the habitable zone is of that star. And so I told you that astronomers are not very good at naming things. So this means that the Webb Space Telescope, which is labeled as JWST there, its successor. So Roman is like an spy satellite that the government said, here, you can have it. I said, okay, great. So on that, there's a test instrument for the coronagraph. So coronagraph instrument that's going to test getting that contrast ratio down. So it's going to test some of the technology to get to dimmer stars, dimmer planets. But HWO is Habitable World Observatory, and that is like the next great mission that NASA is going to have. So you've probably heard of the Hubble Space Telescope, right? This is its successor, basically. And that's not going to launch until the 2040s. So for those of you who are students now, maybe your students will be the graduate students working on this. Maybe their students will, depending on when that is. And so again, when we're thinking about the far future and these worlds that I can't see, there's a lot that we can do once we have the data coming in. There's a lot we can do about the modeling. But in the interim, we do have to use a lot of art and visualization to get from, what we think about a planet like Earth, where, the atmosphere is breathable and we've got luscious vegetation, where you can take off the helmet of your spacesuit, right? To the fact that we can actually see a solar system and a pale blue dot. That is the Earth that Carl Sagan referred to. So there's a lot in between and a lot of work to get there. So I hope today has gotten you thinking a little bit about how you can take your data and go a step further in communicating that story, whether it's the same story you know about Pluto, Neptune, but also what you do when there isn't any data there, right? And how do you fill that gap and keep people engaged? Because sure, we can have artist impressions of things that seem like the movies, but then there's everything from just diagrams and plots and models that can bridge that gap. So I'm going to stop there, and I'm happy to take any questions. Thanks.